This podcast is presented by SCHOTT. With over 130 years of experience delivering innovative, high-quality products, SCHOTT is the global leader in specialty glass, glass ceramics, and other innovative materials. With a direct presence in over 30 countries, the company is a highly skilled partner for several high-tech industries, including defense, semiconductors, data communications, optics, energy, automotive, aerospace, and healthcare. One of SCHOTT's key goals is environmental protection corporate-wide, and it is committed to being the first specialty glass manufacturer in the world to be climate neutral by 2030. Thank you again to our sponsors at SCHOTT for helping us present this podcast to you.
Hello and welcome to the Emerging Tech Horizons podcast. I'm Arun Seraphin, Deputy Director of the Emerging Technologies Institute here at the National Defense Industrial Association. On today's episode, we're going to be taking a little bit of a look into quantum computing and its applications for the Department of Defense. My guest today to help with that discussion is Dr. Pete Shadbolt, co-founder and Chief Scientific Officer of PsiQuantum, one of the emerging quantum computing companies, both in the commercial and the defense space. PsiQuantum is a Palo Alto-based startup building a general-purpose silicon photonic quantum computer. As the Chief Scientific Officer, Pete oversees the application and implementation of technology and scientific-related policy and procedures that are vital to the success of PsiQuantum. A little bit on Pete's background. After earning your PhD in experimental photonic quantum computing from the University of Bristol in 2014, you were a postdoc at Imperial College researching the theory of photonic quantum computing. During your time at Bristol, Pete demonstrated the first ever variational quantum eigensolver, and the first ever public API to a quantum processor. Considerable, fantastic background and awards. Pete's been awarded the 2014 Engineering and Physical Sciences Research Council Rising Star Award by the British Research Council. The Engineering and Physical Science Research Council is recognizing Inspirational Scientist and Engineer Award, and the European Physics Society's Thesis Prize. So join me in welcoming Dr. Shadbolt to today's podcast. Thanks for joining us today. So I tried to do a little bit of an introduction there, but from your own words, tell us a little bit about your background and how you came from doing that hardcore physics work to where you are today.
Yeah, well, first of all, thanks for the introduction and for inviting me to come and join you guys. I really appreciate it. My background is that I'm a technical person, and I worked in university for a long time, and that's pretty well the sort of the origin, and I would also say to some extent the pathology of quantum computing, which is that quantum computing is this decades-old idea. People are tremendously excited by the prospect. It requires you to do things with physics that are novel and demanding, and so PsiQuantum, like most other quantum computing efforts, came out of a university research environment. So as you say, I did an undergraduate and a PhD and a postdoc. And at some point, myself and my co-founders and colleagues got to the point where we had done enough experiments in the university, shown enough of the basic physics and manipulation of qubits and so on, that we decided we needed a vehicle that wasn't a university research group in order to actually deliver on the promise of the technology. So I had an absolutely wonderful time in Bristol. The origins of that story are really that people had been doing photonic quantum computing for quite a long time. If you look at the early experiments on quantum physics, many of those will be done with photons. The reason for that is that photons don't feel heat and they don't feel electromagnetic interference. They're very well isolated from their environment. And so you can play around with entangled qubits and entangled quantum systems at room temperature using relatively cheap optics. So there was a whole tradition of people, researchers buying lenses and mirrors and lasers, setting stuff up on a big bench and showing these kind of basic demonstrations of quantum physics. What we did at Bristol, and specifically my co-founders Jeremy and Mark and a few of the other people there, is they had the idea to move that meter scale bulk optics bench onto a photonic chip. So repurposing silicon photonic technology that had been developed by the telecom industry for optical networking, and squeezing all of this optics down onto a tiny silicon chip. And I arrived at Bristol right when they had gotten started with that activity. And I was so lucky to just find myself in that environment, because suddenly you could print these photonic chips with very complex circuits, entangled photons, and so on. And there was just a huge expanse of opportunity for us there. We could do all sorts of wonderful things with these systems that had never been done before. And yeah, it was just a real joy to work in the lab, do experimental physics, see entangled photons and small instances of algorithms and all that kind of stuff. I was very, very fortunate, very lucky to be involved in that.
So you're working on successful physics research, demonstrating what needs to be demonstrated at the lab bench with your optical table, doing all the things it's working out. It's a big step to then try to say, okay, we can turn this into a business.
Yeah.
And I'm imagining for a set of technical people, that's a big leap. So I'd love to hear about that leap, and then I'd love to hear about the initial conversations with the funder side.
Yeah.
How did someone like you with your technical background sort of get into that part of the conversation?
Yeah, so people have been dreaming of building quantum computers for a long time, for decades, and they have known for most of that time that you're going to need a really big quantum computer to do anything really commercially significant. And by big, I mean somewhere on the order of 1 million qubits. And that was known by the entire academic community for 20 or so years. Certainly was very clear when we started the company. At the same time that we were starting that company, there was suddenly a wave of enthusiasm for kind of hopeful ideas that you might get something done with a much smaller quantum computer, something much closer to the science experiments that we were doing in the university. And you asked about kind of the impetus to get started, to get out of the university, start a company. That really was built around a few key kind of ideas in our mind. The first was that we were really convicted that you need a big one. The first was that after having played around with small systems of qubits, having worked on things like the variational quantum eigensolver, which became a poster child application for this idea of non-error corrected quantum computers, and just played with these small systems for some time, we eventually arrived at the conclusion we're going to need to build a very, very large system. So that, of course, is not something that's going to get solved by a university research group. We were publishing... Just
because of the scale of the problem.
Yeah, because it's engineering, it's not science, is the very glib way to put it. And, the challenge really for a professor of physics or whatever who's starting a quantum computing company is really to throw off all of the previous figures of merit that they've been optimizing for. Professors of physics get rewarded for publishing papers, showing novel things, doing things that are cool and interesting and whatever. Actually, if you have to build a 1 million qubit quantum computer, a lot of the work that you have to do is not, novel or fascinating or whatever. It's a grind. It's, a very expensive grind to get, extremely good device performance.
It's the scientists saying, over to you, engineering, to figure out the parts.
Exactly. And I think, and so when we got started with the company, we had a few very clear kind of ideas. You need a big quantum computer, you need error correction, you need about 1 million qubits. And you asked about bravery. With many approaches to quantum computing, that would have been too brave of a thing to do, right? Like with some of these technologies, they require such exotic materials or operating environments or whatever, that we personally would not have been able to sort of stomach that prospect. Go and build a 1 million qubit quantum computer, whatever, raise money. We were lucky that the approach that we took was based on photonics, which can be manufactured in a high volume semiconductor environment, where of course 1 million is not such a big number. And so we could see...
It's nothing for silicon, right?
Yeah, we could see like a very difficult, but very, very sort of challenging, but plausible path to getting to that kind of scale on a time scale that was acceptable to venture capital, basically like a reasonable.
So in that dealing with the venture capitalists and trying to explain the advantages.
Yeah.
I imagine then that's another translation function, right? Those guys are good at a lot of things. I'm not sure they're great at solving equations. So how did those initial conversations go?
Yeah, so this was not my personal sort of, I didn't architect this thing, but I think what what was really fascinating to watch over the years that we've been, running this company, raising money, etc., is the following. Scientists have an idea that venture capitalists are very short-term oriented, are not particularly technical, and they just want to see some kind of awesome result really quickly. And so when we arrived in Silicon Valley, we could very easily have taken the experiments that we were doing in Bristol, shown those experiments and said, hey, look, we're going to scale this up by a factor of 10. We'll get to about 100 qubits. We'll do some awesome demo. We'll put it on, some cloud computing service, and we'll be in great shape. And that would have been the thing that would have been designed to be attractive to venture capitalists, right. I think.
Right.
We did the opposite. We said, you need probably about 1 million qubits. You've got to have error correction. You've got to be building that in a huge, really expensive factory. This is just something else. This is in a different category. And by the way, there are no intermediate scale systems before 1 million qubits that do anything useful. And so we came with this very contrarian, fairly aggressive pitch that was honestly delivering quite a lot of bad news to
out of their
people.
Style for people who fund software.
And right? A lot of people that we spoke to, cloud services and whatever, a lot of people that we spoke to, of course, took a look at that, and very smart people, whatever, but they took a look at that and said, this is not for us, right? This is not our thing. We were extremely lucky, really, to find a handful of people who could pattern match on the fact that we were saying something that was true, and that we were sort of clear-eyed about a path to get to a real, genuinely valuable quantum computer. And so, to give you a feeling for it, one of our investor board members has a PhD in optical quantum computing and a postdoc in ion trap quantum computing with a Nobel laureate. Another one has, lasers in their basement and whatever. It's a pretty special group of people who we encountered. The other thing that I would say is that these were the early people when we first showed up in Silicon Valley. There's a very offensive narrative that I often hear, which is of course, your Series A venture capitalists are going to be, nerdy people who understand the technology pretty well and, are thrilled by the, fascinating aspects of what you're doing. But just wait, right? You often hear this when people are giving you advice, just wait. Later on, you're going to encounter people who are writing bigger checks and who are inevitably much less, whatever, excited. Of course, our story, that contrarian story, which is don't focus on physics novelty, focus on high volume semiconductor manufacturing and infrastructure and concrete and steel, because those are the things that are actually stopping us from delivering on real quantum computers. That story is contrarian. It's not kind of flashy, but it was, of course, instantly understood by the people who write big checks later down the road, because they are the same people who built the semiconductor industry, built the automotive industry. They understand how to pattern match on, some of the more mature, sort of aggressive aspects of.
They've seen this path
of how we're going about things. Right. Now, of course, there are still very challenging technical risks and all sorts of things under the hood that need to be examined. But that general approach of just telling people what is actually required was turned out to be successful. Yeah.
So at the same time as you're pursuing those commercial funding options, then you've also begun to work closely with the Department of Defense.
Yeah.
So tell us a little bit about how you're working with the Department of Defense at this point, and then why does it matter? Why does quantum computing, you think, matter to the Department of Defense?
Yeah, so we have an activity with DARPA, which we recently announced. We also have an activity with AFRL.
Air Force Research Lab.
Air Force Research Lab in Rome, New York. And both of those are relatively new activities, and they're in really fantastic shape. So the technical counterparts that we have, as well as the non-technical counterparts on those activities, are just awesome, strong technical people. And we're spending a lot of time with both of those groups of people. Really just, we're a pretty big team now. We've been around for 7 years. we've done quite a lot of work, I would claim, over that time frame, and it's a lot of work to then show people what you've done. But I'm very glad that we're doing that, and very excited to sort of have that relationship active. Yeah.
And it's been an area of focus for senior leadership in the Pentagon and the White House for multiple administrations now, as well as Capitol Hill, legislation and funding provided to support the general area. It's definitely an area where we should consider the U.S. being in a global competition. Is that fair to say?
Yeah.
So where would you say we are the U.S. and our friends relative to, let's say, China, Russia?
Yeah, I think people recognize that quantum computing has the potential to be a technology that changes things in the same way that conventional computing did, that other sort of generic technologies had profound impact and ultimately ended up sort of distributed throughout our lives. I think that people see quantum computing in that same way, and we have seen very large investments by governments around the world, billion-dollar type investments around the world, to accelerate quantum computing. I think that in pretty well every case, that money has been very well spent in funding research, in funding academic activities, and sort of bringing up the level of capability for all of these different technologies simultaneously. There are many different competing approaches. Quantum computing is difficult in that there's a lot of ways to do it, and everyone will tell you that their way is the best way, right? Of course. And so I think what governments have done so far has been very effective, in bringing up the level of capability, but that's not enough to get you to a real quantum computer. That in and of itself is not going to deliver on what really needs to be a building scale system, data center like object. That requires like a change of tone and a change of approach. And honestly, I think we're not there yet. Like, I haven't seen any government anywhere in the world really start down that path of, we are now building a real fault-tolerant quantum computer.
The scale-up part of it.
The scale-up part. Yeah.
So let me, historical example, maybe this is totally wrong, but it was the government that helped scale up traditional high-performance computing.
Yes,
right?
absolutely.
Supercomputing.
Absolutely,
at places like the Department of Energy National Labs.
Yeah.
I guess, couldn't I argue that there's the same important set of missions and the same need for government intervention to get that kind of scale up done? Or is it the case that the commercial sector will do the scale up? Where do you think that? Where should I be on that?
It's a good question. So I think it is perfectly conceivable that a commercial entity gets there. I also think that based on your historical example, as well as various other pertinent examples, it would also be quite strange if that happened. And my personal view here is that, again, our conviction, which is not shared by everybody, there are very smart people who disagree with me on this, but our conviction is that a real quantum computer is going to be a huge facility, like a big building that's anchored into the ground and very expensive, and there's going to be a very small number of those things. My view is that that's going to start to function strategically with the same sort of dynamics that we see around semiconductor manufacturing. So fortunately, it's a little easier to tell this story because there's so much awareness at the moment, but the semiconductor manufacturing has exactly this problem. It's incredibly centralized. It's one of the most centralized technologies that humans have ever come up with. There are very few fabs on planet Earth that can actually deliver on serious advanced semiconductor manufacturing capability, and the location and access to those things becomes hugely strategically important. We think that quantum computing is going to go the same way. And so if you are a government and you believe that, then you probably want to reflect on the situation that we are currently in with semiconductor manufacturing. And I would suggest that it would be in the United States' interest, for instance, to make sure that there is a quantum computer.
Both in a national security and economic competitiveness
standpoint.
Yes,
both.
So then there's like every technology area and every new emerging technology, there's a set of naysayers.
Yep.
Who at least are preaching caution.
Yep.
So realistically, for an NDIA member, a big company or a small company, what things should they be looking for to see that there's real progress being made here, relative to whatever competitor computing technologies there might be?
Yeah.
And when should they expect to see those kinds of signals?
Yeah. So there are a whole ton of naysayers, and some of those are more nuanced than others, let's say. But I'm very glad that they all exist, because quantum computing is a space that, as you know, has got a ton of hype in it, all sorts of mad stuff going on. It's very easy to just attach the word quantum to things and then get overexcited about them. The reality, the truth, in my opinion, is that quantum computing is just incredibly complex. And there's a piece of bad news for you. Like, I would love to give you an easy answer. The bad news is it is really complex, and to do a genuine assessment of somebody's claims or something's viability or whatever, it's probably a pretty involved activity. And that's exactly why, we are, for instance, spending a ton of time with DARPA at the moment, is they actually have the resources and the size of team and the capability and the technical knowledge to be able to do this type of assessment on what we're up to. If there's one thing that I would push for people to look for that sometimes falls by the wayside, it's really maturity. In quantum computing, people love to compare the qubits. They love to argue over who has the best qubit, and every professor will be coming with their own qubit and saying, my qubit is super awesome for this reason, and it's better than everybody else's qubit. And I often have to I often tell people, in my view, the reality is that everybody's qubit is actually pretty nice at this point, right? Like, whether it's superconducting qubit, quantum dot, photon, ion, everyone can run those things with decent fidelities. They can build them, they can fabricate them, they work, there's nothing wrong with them. We'd like to make them a little more performant or something, but people obsess over these kind of, because they can make a table where they can compare these things and then try to pick a winner. I don't put too much weight on that. What I really think is underrated is maturity, as we were discussing earlier. Okay, take that qubit and now figure out how you're going to build millions of them, and how you're going to test millions of them, and how you're going to make that reliable, and how you're going to control a system at that scale. None of that is particularly sexy or attractive to, like, the editor at Nature or something like that. Mm-hmm. But it's really, really important. It's absolutely necessary. So yeah, I would say if you are evaluating a quantum computing effort, look for signs of technical maturity, as opposed to a sort of catchy advantage that they might have. Yeah.
So if I project myself even further in the future, right after the technology has matured, and it's you're saying that companies, NDIA member companies, they're not going off to buy a quantum computer for their desktop. They're making use of a service. Is that the way this will manifest itself?
That's right. That's right. Yeah. So of course, in conventional computing, people famously made these mistakes of saying that you'll never buy a computer and it'll never fit in your desk and whatever. And they were wrong. I will make exactly the same statements for quantum computing. I think I'm right, but we'll see. Like, time will tell.
Okay. It's recorded now.
Yes, it's recorded. I think they're going to be big for a really long time. Let me put it that way. With that said, yes, it will be a service. You will, send code to the machine over the internet. The thing that...
And why is that? Tell me about the advantage there, because I can already go to a high-performance computing service, right? Yeah. Or pretty good local services, right?
Yeah, so the advantage with quantum computing is very simple, which is that for some applications, the thing can give you an answer in a sensible amount of time, meaning days or weeks or something like that, where it's going to take longer than the age of the universe for any conventional supercomputer that human beings could ever build to give you an answer.
What's an example of a problem like that?
So the best advertised example is for code breaking, for factoring large integers. But there are a long list of other applications that are being investigated to varying degrees of completeness. many of those focus on materials, physics, chemistry, simulation type problems. There is a big body of work on optimization problems. There's a big body of work on partial differential equation solving, things related to finite difference methods, things related to, basically a diversity of things in physics, chemistry, material science. That's where you find.
So could you see in the future then a middle-sized company, NDIA member, who's somewhere in the supply chain in propellants or advanced materials, or an engineering firm, making use of these kinds of services sometime in the not too distant future?
Yeah, so PsiQuantum today works with a whole bunch of corporations, Fortune 100, Fortune 500 type companies.
Solving real problems.
We do not solve real problems. We do not have a quantum computer today. PsiQuantum does not have a quantum computer. We have what we think is extremely exciting progress and a great roadmap to a quantum computer. Today, we're working with those customers really on the code and the math and preparing them for the existence of that large-scale machine when it arrives. But yeah, those are exactly in that sort of category. Like companies who want to use the quantum computer, they don't expect necessarily to buy their own quantum computer. They expect to be running applications remotely.
So let me just click on that for a second.
Yeah.
There are people who are selling quantum computing services today.
Yes.
What would you say about those services? Politely, I suppose.
Yeah. So I think it's. I'm British, so I'm supposed to be, especially I'm British in America, so I'm supposed to be extra polite. I think it's awesome. I think it's unreal, right? I feel so lucky that I got involved in quantum computing 15 years ago, something like that. And during just those 15 years, which is a very short time, really, I've seen us go from doing experiments in the lab to there being multiple different services where high school kids can sign into AWS or Google Cloud and get access to a real quantum computer with more entangled qubits than I could have dreamed of when I was a PhD student.
Right.
And they can program these things in Python, and there are endless textbooks and endless GitHub repos and whatever. Anyone can do it today. Get on the internet, program a real quantum computer. Now, the problem is those things are way too small to do something really, really valuable.
Right.
But I think it's pedagogically incredible situation.
Right.
And it also is really important for the sort of hype and, risk of these types of very bubbly, exciting new technologies. It's really important that people can get their hands directly on it, see the technology, validate that it's real, see that the qubits are genuinely entangled, whatever. It's very important that happens. We don't do that. We took a very sort of extreme strategy, which is just, we're going to spend every dollar and every hour trying to get to a large scale system as fast as humanly possible. And that's kind of the promise that we make to our funders, right? Is if you give us money, we're going to spend that exclusively on trying to get to a very large scale machine. And we're not spending time on anything else. On that note about the introducing people to the promise of quantum computing with today's machines being a good educational sort of effort. Parallel in my head is I learned to program on TRS-80s and Commodore 64s, Apple IIs. Yeah.
And then someday got to use bigger machines as they actually appeared and got to exist. There's some parallel in that.
Yeah.
It also, I guess, shows you the promise of what could be possible, right? And help shape the development of
I think so,
the technology. Does the field of computer science, does coding itself, is it going to need to change because of the new machines?
Yeah, so I personally have, again, a contrarian, annoying perspective on this. What people love to say is it's a new type of computer, and there's an immediate fascinating question as to how you program that. And it's very tempting to spend a huge amount of thrilling intellectual energy on what would the best programming language look like for a quantum computer, and how are we going to orchestrate these things and whatever. The reality is that if you go on GitHub today, you can go and find literally hundreds of repositories where you can program quantum computers in very mundane programming languages, Python and JavaScript and C++ and whatever. And those languages are just great for programming against, a 30-qubit simulator that you can run on your laptop. Well, as far as we know, the sort of dream quantum computer that really starts to have profound impact only has hundreds of logical qubits. So like this dream system that, to your analogy, one day you're dreaming of programming, it's only like 5 times bigger or something than what you can play around with on your laptop. Of course, it's 2 to the power of 60 or something times bigger in terms of the state vector. So it's astronomically more powerful in some sense, but it's only a few times bigger from the point of view of a programmer perspective. And these existing programming languages, compilers, whatever, pretty awesome already for those things. So there's still lots of work to do to make them better. But I don't see it as like a wholesale reinvention of software engineering or something like that.
So let's sort of bring this in for a landing here.
Yeah.
If you could advise the Department of Defense or the Congress or the White House on what the next logical steps are to either just continue what they're doing or to do something different at this point to support efforts of your company and other companies, what kinds of things would you want them to do?
Yeah, so I think there's already, of course, quantum computing is a huge community and pretty sophisticated, kind, friendly, interesting community of people. And there's very good representation already from people who are asking, for instance, for workforce development. So this is, widely publicized and sort of well understood.
What are the workforce needs?
Quantum physicists, basically, whether that's experimental quantum physicists or especially algorithms people. So typically a sort of PhD in quantum information who knows how to program a quantum computer. It's a pretty rare capability, especially if you want them to be really, really good. And so there's been various broad pushes for that sort of thing. Workforce development. There is a big piece that's especially close to our hearts in semiconductor manufacturing, and of course the CHIPS Act and so on is very good for a whole diversity of quantum computing efforts. People need to make fairly unusual chips. They need to go outside the bounds of a typical semiconductor fab. And so I think we'll see a whole load of healthy output from that. Again, our sort of obsession at PsiQuantum is really with the idea that you need a big quantum computer. And that requires a different sort of attitude and infrastructure, concrete, steel, high power cryogenics. These are the types of things that we selfishly care about. But I think it's also relevant for any quantum computing effort that is getting real about building a large, valuable system. There's a good alignment of interests around those topics.
And then the question of how quickly does the Department of Defense have to be thinking about security related to these things? This is an emerging open science field at this point for the most part.
Yeah.
Can it remain that way? Does it have to go classified very quickly, completely? How do we draw the line there?
Yeah, so I think there's probably 2 things to say there. The first is that lots of good things are already being done. So NIST, for instance, has a competition to find quantum-resistant cryptography methods that you could run on conventional hardware and that would secure information against the existence of even a very large quantum computer. So that should help people to sleep at night, and is very, very good news. The other thing that I would say on that topic is that quantum computing has the same property as many different technologies, which is that you can wield it for a whole diversity of different applications. You can use it for things that are completely benign. You can use it for things that are scary. There is a very wide range of things that can potentially be done with this technology. In my view, I hope that the future is very much in the same category as things like GPS, radar, the internet, etc., which is that these were all technologies that came out from, somewhere in the military-industrial complex, and all were, controlled and in some sense scary when they first emerged. But of course, I've got GPS in my phone, and I'm regularly using the internet, which, by the way, is in the same category. And we have radar on commercial aircraft and so on. So I think these technologies ultimately came out into the open, and people realized that the upside was much, much greater than the downside, and that if used responsibly, they could be good for everybody. And I think, I hope that quantum computing goes the same way.
So we're going to have to call it at that,
Yeah.
but I'll invite you back when I have the portable quantum computer in my pocket, just to say you were wrong about that part of it as well. And how much it's being commercially used. So with that, I want to thank Dr. Pete Shadbolt for joining us today for this discussion of quantum computing. Thank you so much for tuning in. I want to take a moment to highlight our upcoming Emerging Technologies for Defense Conference and Exhibition, which is going to be held in Washington, D.C. this summer at the JW Marriott, August 28th to 30th. Look for more information on our website coming soon. Thanks for joining us on Emerging Tech Horizons.